Welcome to lecture 11. So, in this case, we will take a look at the constraints that are introduced by the sharing of resources among tasks in the sense that if we have multiple tasks and we have a single resource, and let's say a task locks a resource preemptively, then what happens, right? What are we supposed to do in that case? If let's say the tasks need resources and need to acquire resources. So far the only resource that we have considered is the CPU, and that too a single CPU which is serially reusable, which means that one task runs and then another, right? Then another and so on. So it is serially reusable. So, our condition, which was our utilization condition, the summation of utilizations is less than equal to 1, was dependent on this premise that the sum of utilizations is bounded by 1, which means at any one point of time, only one task can execute on a CPU. And furthermore, a task can be preempted at any time by other tasks, other high priority tasks, without affecting correctness. So, in reality, tasks also need to share other kinds of resources other than the CPU. For example, they may want to share files, they may want to share data structures, they may want to share other devices, which are non preemptible resources in the sense if a task is holding on to something, it may want to continue to hold on to something till it has completed its execution, right? So these resources themselves may not be of the type, something like a printer. So you can't really preempt a task in the middle of printing a page. So either it will not print a page or it will print the complete page. So, preempting a task and restoring it later may not be possible with many kinds of devices. So, any piece of code in which a shared and non preemptible resource is accessed is known as a critical section in the OS literature in the sense that we come here, we execute the entire critical section known as the CS, and then we exit it. So, no program would actually exit the critical section in the middle and resume that later. This is typically something that we like to avoid, even though sometimes we make an exception. But the main idea is that the critical section is where one thread is supposed to be there and it is supposed to finish the execution, you know, preferably in one go. So in the critical section execution, traditional operating system solution to execute a critical section is like this. That we use semaphores. So we use locks and semaphores. Of course, semaphores are generalizations of locks. So we either use locks or semaphores, where the idea is that if I've acquired a lock or semaphore, I get the permission to execute the critical section. And of course, at the end, I exit, right? So this is the standard way in which this is done. However, in real time systems work, this solution does not work very well. And it results in what is known as priority inversion and unbounded priority inversion. It basically means that low priority tasks get to run on the CPU, and high priority tasks, right, they don't get to execute on the CPU because they are waiting for some resource which is not becoming free, right? So this is known as priority inversion. We'll take a look at this later, but this is the broad idea. If we use a similar solution as is used in a regular operating system in a real time operating system. So what is priority inversion? So assume a task is executing a critical section, it cannot be preempted. So what happens is that if a task is in a critical section, then a higher priority task will keep waiting, because the reason is that the low priority task TL is in the critical section. It cannot be evicted or from the CPU or preempted at this point of time, which means that in the waiting queue we have high priority tasks which are waiting for the low priority task to finish its execution. So one thing you need to keep in mind is that something similar was not happening In the case of RMS or EDF, the reason being that whenever a high priority task arrived, we could immediately preempt the low priority processes, and because of that, we were able to avoid priority inversion. But now the fact that this critical section has come in, this is what is precisely causing the problem. In the sense, this is what is keeping high priority tasks in the waiting queue, even though they can execute, primarily because something of a non-preemptible resource or device or piece of code is being accessed within a critical section, and all of them need to wait for the critical section to finish, for the low priority thread to finish executing the critical section, as you can see over here. Now let us look more at priority inversion. So when a resource, consider a resource that needs to be shared in the exclusive mode. Exclusive mode basically means only one task can own it. So it is possible that a task, a high priority task particularly, may be blocked by a lower priority task which is already holding the resource. So what will happen is, because a low priority task is holding the resource, a high priority task will remain waiting. This is something that we have seen in the previous slide, right? That the what you see over here in the diagram is that the high priority task TH is waiting for the low priority task TL. So now let us define another term known as unbounded priority inversion. What you just saw in the previous slide is bounded priority inversion, but we'll talk about unbounded priority inversion. So consider the following situation. A low priority task is holding a resource, right? So task TL is holding a resource. So let's see, if it's holding a resource, we'll add an arrow from the resource to TL. And a high priority task is waiting. Okay. So then the key point is that if the high priority task, in this case TH, so we are referring to as T2 and T1 also, or let's say TH is waiting for TL to become free. So what could happen is that an intermediate priority task, so let's call it TI, which does not need the resource, can basically preempt the low priority task from the CPU, not from the resource that it is holding, but can preempt the low priority task from the CPU and it can execute. So we can have hundreds of such intermediate priority tasks which will preempt the low priority task and they will keep on executing, but the high priority task will not get to execute. The reason being that it has another dependency other than the CPU on the low priority task which is still holding on to the resource. So sadly, it is not able to relinquish the resource because it is not getting CPU time. Why is it not getting CPU time? Because other intermediate priority tasks are evicting it from the CPU and they are executing. So an example of unbounded priority inversion will be something like this. So let me slightly proceed through the animation, then I will show you. So let us now understand. So let us say that we have we have a high priority task T1 and the lowest priority task is T6, which has held a resource. So when T1 comes, it will not be able to execute because the resource is held by T6, so it will wait. But then what will happen is a bunch of other intermediate priority tasks will come who have a lower priority than T1 but a higher priority than T6. So they will all execute. As you can see, the blue, they will all execute. Finally, at one point, T6 will get the time to execute, so it will unlock the critical resource. And that is when you will see that T1 will get a chance to execute. So this phenomenon is known as an unbounded priority inversion, as opposed to a simple priority inversion that I was discussing, just before the previous slide. So here what will happen is that a very large number of tasks can execute before actually T1, which is the highest priority task, can execute. And the reason is because of this resource dependency on CR. So this is known as unbounded priority inversion. So what is the number of priority inversion suffered by a high priority task? It actually can be too many, in the sense it can be large enough, which will actually cause it to miss its deadline. And the only fault of it is that it is unfortunate for it, of course, that one of the lower priority tasks, in the case of the previous example, the lowest priority task T6 is holding on to the resource, and because of that, everybody gets to execute other than T1. So, one of the most celebrated examples in this case is a Mars Pathfinder. So, those who are my age would know that the Mars Pathfinder was a rover, right, which was meant to which was sent to Mars, and there it was meant to scan the Martian surface. So that did have some bugs of this kind, right, which led to a significant disruption in its performance. So coming to an example, suppose that tasks tau 1 and tau 3, or T1 and T3, share some data which is in exclusive mode, in the sense the data is a critical resource and it is accessed within a critical section. So access to the data itself is restricted using a semaphore X. So each task would end up executing the following code, which is to do some local work, wait for semaphore X. So PX, actually, if if this is the terminology that you'll use. So it will basically wait for the semaphore to become free, then access a shared resource, right? Access the shared resource. So I just cleared up the clutter on the slide. So at this point, after accessing the shared resource, the semaphore is freed, in the sense the semaphore is signaled. This is traditional operating systems literature. And then the thread can do more of local work, right, after accessing the resource. So if I were to visualize the same, what we would see is that, let's say, a thread is doing some local work. It gets access to the resource, so it does some work on the resource. But let us say then a higher priority thread preempts it. So the higher priority thread then does local work, but for some reason it gets blocked. Right? So why does it get blocked? It gets blocked because it needs access to the resource, and this is there with thread T3. So the higher priority thread cannot proceed. So let's say after this, thread T3 starts to execute. So when it is executing, you need the CPU as well as the resource. So it continues to access the resource. After that, the resource is freed. Once the resource is freed, the higher priority task, which is task T1 in this case, can start executing. So it will get access to the resource and will start executing immediately. After this, it will do some local work and it will complete. Once it completes, assuming T3 is the most high priority process right now, so what will happen is T3 will start executing. So it will start accessing it will start doing some local work and then it will complete. So this shows you the interaction between T1 and task 1 and task 3, where task 1 has a higher priority, but it gets blocked. There is a priority inversion because task 3 gets access to a resource that task 1 actually needs at a later point of time. See, if I were to look at two priority inversions, the way it would look like is that task 3 will do some local work. It will get access to a resource and then it will get blocked. So it will get blocked for exactly the same reason that it didn't get access to the resource. But in this case, we are looking more at an unbounded priority inversion kind of scenario, where an intermediate task, which is task 2, starts to execute. In the sense, it does its local work, and so which is neither T1 nor T3. In the sense that the resource is still captured by T3, and because of that, T1 is waiting. the most high priority process. But after T2 completes, again T3 task 3 gets to execute, which as you can see is a long time later. It works with the resource, then it relinquishes the resource. Task 1 begins, it works on the resource, does some local work and completes. So this is exactly how you can have unbounded priority inversions. So in this case we see two. So of course if for an unbounded situation, what will happen is that instead of one intermediate task, there will be a bunch of intermediate tasks where again T3 gets the resource but gets preempted by T1. T1 blocks, and after that, a bunch of other intermediate tasks execute. A long, long time later, T3 executes. And then what we see is that at this point of time, again T1 executes, it gets the resource, and then it finishes its local work. But it's very well possible that it misses its deadline because it got delayed for such a large period, right? If you see such a large period for which it got delayed. So what happened with the Mars Pathfinder is that it landed on Mars on the Martian surface on July 4th, 1997. So this part went seamlessly in the sense it bounced onto the Martian surface with airbags. It deployed a rover which gathered and transmitted a large amount of data back to Earth, which included, quite panoramic, iconic pictures of Mars that we have. So all of this is courtesy Pathfinder. So these are again, another panoramic view of the Martian surface. You can see the Martian soil, the rocks. But unfortunately, it began experiencing total system resets. Each of these resulted in a loss of data because in a system reset, some data was getting lost. So the newspapers reported these failures as software glitches. And basically the way that the failures got reported is that the computer was trying to do many things at once and it was not able to do that. So the real-time kernel that was used was VxWorks by Wind River Systems and RMA scheduling was used. So we are an expert on RMA by this point. So Pathfinder contained an information bus, which was basically a shared memory, right? A bus with a shared memory. And this was used for passing information between the different components of the spacecraft, the processing components, memory components, storage components, and sensing components. So the VxWorks real-time operating system. So the VxWorks operating system can be run in trace mode, where it captures and it logs. So why do you log? So you log for future debugging and analysis. Interesting system events such as context switches, the use of synchronization objects, and interrupts. So the engineers of Jet Propulsion Laboratory, they spent hours running an exact replica of the spacecraft in the lab, and they were able to replicate the precise conditions under which a reset occurred. So, what we need to focus on, or rather, they focused on, was the VxWorks mutex object, which is the lock object. So, basically, this accepts a Boolean parameter, which essentially says whether priority inheritance should be performed or not. So, if you go back to the previous lecture on RMA, we did talk a little bit about priority inheritance. There, of course, the key idea was that if a low priority thread is blocking a high priority thread for whatever reason, then the low priorities thread's priority is temporarily jacked up, such that these priority inversions don't occur. In the sense, no other intermediate thread is able to swap it out. So it was clear to the JPL engineers that if we turn on priority inheritance, then these resets will be prevented. So because this was a configuration time parameter and it was off, so that is why they conjectured that these resets are happening because tasks are missing their deadlines. So they uploaded a short C program which had these initialization parameters right? And they were global variables to the overall Pathfinder ecosystem. So they uploaded a short C program and executed it on the spacecraft. So not on the spacecraft, on the rover, basically. So then, uh, this did solve the issue to a large extent. So it also tells you that in such sensitive systems, how much of a problem is priority inversion and unbounded priority inversion. So solution for a simple priority inversion is that we need to first analyze, and we'll look at the fact that the longest duration for which a simple priority inversion can occur, it is essentially upper bounded unless of course there are intermediate tasks by the maximum amount of time that the lower priority task needs to access the resource, and that too exclusively. In the sense that if we assume the worst case, which is that the low priority task got access to the resource, and exactly at that point of time the high priority task came, it tried to immediately grab the resource and it couldn't, then the amount of time that it will wait will be exactly the time that the low priority task will be accessing the resource. So, in many ways, a simple priority inversion can be tolerated if this duration is not too large, right? And so, what we can do is we can look at engineering solutions where we limit the time for which a task executes this critical section. In a certain sense, we work on the resources and we reduce the time for which the different tasks actually use the resource exclusively. So, in this case, with efficient resource design, with careful programming that takes such situations and scenarios into account or into consideration, a simple priority inversion involving only two tasks, where essentially one task is grabbing a resource, and for the duration of the time that the resource is being used or processed, whatever you may call, the high priority task is waiting. Such a situation is not a big deal. In a sense, our deadlines and our safety margins can be adjusted to take that into account, right? So, in a certain sense, it's not a big deal. However, unbounded priority inversion is a different, is a problem in a separate class. So, we have already discussed this where a low priority task holds a resource, a high priority task is waiting on the resource, that is, right? So, the resource is with a low priority task and a high priority task is waiting. And then an intermediate priority task which does not need the resource preempts the low priority task and it executes. Because there can be an unlimited number of such intermediate tasks, and these are periodic tasks, right? So you can't say that one task you execute and it is done, because it can appear once again after its period. So this is when you can have a large delay which will cause the high priority task to miss its deadline. So a quick graphic about unbounded priority inversions. We have already seen that. I will not describe this more, but the key idea is that TL, the low priority task, holds the resource. TH waits for it, and these are all the intermediate tasks which enjoy the party. So naturally, the number of priority inversions is important in such a problem because it can become unbounded. It can cause a task to miss its deadline. In the worst case, the high priority task will have to wait indefinitely, which means it will miss its deadline for sure, regardless of the deadline. So, we end this lecture here just by posing this question, that what do we do with priority inversion? What do we do with unbounded priority inversion? And what exactly are the solutions, right? So, these are things that we would like to explore in the next few lectures with regards to what are the protocols to take care of these problems.